Next, we're going to take a look at a certain class of problems that involve physical systems that have multiple components, each of which are changing in time. So oftentimes in applications, one encounters systems with many different moving parts. So the natural question arises, how do we quantify the rates of change of some of the components of a given system in terms of the rates of change of other components? For example, suppose you're pulling a boat toward a boat dock. You're pulling the rope in at a certain rate, maybe 8 inches per second, something like this. How quickly is the boat approaching the actual boat dock, given that the rope is at an angle with the water line? Another example might be you're running or you have a clock, two clock hands, right? So the clock hands are both moving around the clock face as a function of time. At what rate is the distance between the two clock hands changing? If you have gravel being dumped on a pile and the pile's becoming larger and the gravel's being dumped onto this gravel pile at a certain rate, at what rate of change is the height of the pile changing, given that you know the rate of change of the volume because you know the rate at which gravel is being dumped on a pile. So when you have several different things going on that are not independent, they're related to each other by some basic constraint equation, and you know the rate of change of one of the components, how can you use mathematics and calculus to find the rates of change of the other components? So these sorts of problems are known as related rates problems. So in this video, I'm just going to go over some of the basic problem-solving strategies that will allow you to go out and tackle your first related rates problems. So the first step in general for problem solving is read the problem. Read the problem very closely, very carefully, see what is saying, try to visualize the problem. So there's lots that goes into just reading the problem. Visualize the physical situation that's happening. If you have, like, say, a cone that's changing in time or a snowball, draw a picture of a cone or a sphere. Try to draw a visual picture of the actual physical setup. That will help you go about visualizing and analyzing the system. And also write down all of the information that you're given. Right? If they say that the radius is changing at this rate, write down radius is changing at that rate. If they say this, write down that. If they say the diameter is 5 inches, you can say diameter equals 5 inches. And if you're going to be using the radius later on, make sure to divide 5 by 2 to get the radius. But basically all the information that they give you, write it down, read the problem, understand what's going on before you even try to solve the problem. Another thing, when you're given information about the rates of change, often in a story problem it will say the distance is decreasing at a rate of 5 feet per minute. Okay, so the rate of change, the derivative, is going to equal -5. So pay attention to words like increasing or decreasing that might tip you off onto the sign of a derivative. So you don't want to just, if you're kind of carelessly glance over the words, distance is decreasing at 5 feet per minute, you might say, dr dt equals 5. But it says it's decreasing, so it should be -5 because the distance is decreasing, not increasing. So pay attention to those sorts of words. 2, draw a picture. I already discussed that a little bit. Make sure to write, just get a visualization of what's going on in the problem. The third step, identify quantities that are changing in time. So related rate problems, there's always an implicit independent variable. So the main physical variables are all functions of time. So if it gives you the radius and an angle, and something's moving at a given radius and angle, think of the radius as being a function of time and the angle as being a function of time, because related rates problems basically always are for the purpose of analyzing specific physical situations. This is moving that way, this is moving this way. How is the rate of change in time of this variable related to the rate of change in time of that variable? So a very important step is when you have your picture and you understand the problem, which variables are changing in time. So this can be subtle because you're given things like, oh, maybe the boat dock is 4 feet high. Well, that variable is not changing in time unless the water level is changing, and if you're just pulling a boat towards the shore, you're probably not going to take into account fluctuations of the water level due to the tides, right? That's not, for the purpose of just pulling a boat to the boat dock, you're going to think of the water level as being a constant height. So sometimes they might give you numbers for things that are constants and then numbers for other things that are actually changing in time. So you want to just go through and think about, okay, would that variable be changing? Oh, that's just the length of the clock hand, right? That's just the length of the hour hand and the minute hand. So those lengths aren't changing because a clock hand, the hour hand and minute hand just go around the clock, and the hands themselves don't change in length. So just think about, is this changing, is this not changing? 4, assign variables. And essentially we want to assign variables to the quantities that are changing in time. And it's also good to just spend a few minutes thinking about the way to assign variables. Can you get away with assigning fewer variables? In certain situations, you don't want to assign too many variables because then you have constraints that relate those variables and then upon the constraint that they're actually looking for in the problem. So an example of this is, suppose you have a station like this, like an air traffic control station, and you have one plane up here going this way and another plane down here moving that way. Well, this plane is so many miles east of the station and so many miles north of the station. And then this plane is so many miles west of the station and so many miles south of the station. So you could say, well, and let's say you're just trying to figure out the rate of change of the distance between the two planes. Like, at what rate is the distance between the two planes increasing? Well, one way to go about this is to say x1 and y1 are the positions of plane 1. So you have x1 is this distance, y1 is that distance, x2 is this distance, and y2 is that distance. So x1, y1, two variables both changing in time to give the position of plane 1, x2 and y2, two variables both changing in time to give the position of plane 2. But now you have 4 variables, and what's your distance equation? Well, you can try to write it down. Essentially you have a right triangle like this. So it's x1 plus x2 quantity squared plus y1 plus y2 quantity squared square root. Now it's simpler to just say let x be the total east-west distance between the two planes and y be the total north-south distance between the two planes. And depending on the way the problem is written, you can actually figure the problem out in terms of x and y instead of using x1, y1, x2, y2. So this is just kind of a quick example, but you can see, in some situations you might have an initial tendency to say, oh, x1, y1, x2, y2, or let's do this, 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 and this for our variables. But with a little bit of thought, you might say, oh, well, we can actually get away with a smaller subset of variables. So if you can get away with a smaller subset of variables, do it, right? Because the formulas that you come up with are going to be easier, the analysis is going to be easier. So if there's anything that you can do to come up with a smaller set of variables, do that. Like say if you don't want to, for example, if you have a circle that's growing and shrinking in time, maybe it represents some sort of cell that's increasing or decreasing during some sort of cell activity, like a biology problem. So you wouldn't want to use the diameter and the radius both as independent or dependent variables, right? You don't want to have, okay, well, the diameter is equal to this, so d of t, then we have the radius is equal to that, r of t, because it's a simple relationship between radius and diameter. The diameter is just twice the radius. So why have equations involving d and r plus whatever variables are changing in the problem when you can just get away with just using the radius, right? Maybe they said the diameter is this and then the radius is doing that. So maybe at first reading of the problem, it sounds like you have the diameter as one variable and the radius as a second variable. But really, it's such a simple relationship between the two. Just use the radius. It makes writing down the equations and trying to analyze them simpler in the end. Now that you have the variables, identify the constraints. So with a related rate problem, there's always going to be some sort of constraint between the different variables. By the way, in this example with the airplanes, another variable is going to be d. So the distance between the actual two planes, because I guess the details of this aren't important at this moment, but you're trying to find the rate of change of the distance, so you're looking for the derivative of some function d, where d is the distance between the two planes. So identify the constraints. So is there something that links the variables together, right? So if you have, like say a wall, and you have a ladder that's being pulled away from the wall. So you're pulling it away at this edge, and then the top's going down like that. Well, the ladder is a fixed length. So if your variables are x and y, your constraint's going to be x squared plus y squared is equal to L squared, where L is your fixed length of the ladder. So there's a constraint equation that relates your several variables that are each changing in time. So the constraint equation is going to be very important, because from that we're going to derive the related rates equation. So then 6, determine the related rates equation. And you do this by differentiating the constraint equation. Implicitly with respect to time. So remember, all of your variables, if you have x, y, L, R, D, H, whatever, they're all implicitly functions of time. So everything's changing in time. So it's just like implicit differentiation, except every time you do a derivative, if you're taking the derivative x squared, it's going to be 2x times a dx dt. If you're taking a derivative of y cubed, it's going to be 3y squared times the dy dt, right? So whenever you take the derivative of anything, you're going to use the chain rule and throw in the derivative of that variable with respect to time. And the resulting equation is called the related rates equation. So it's a single equation that relates the rates of change of your physical variables that are each changing in time. So it relates the values of those variables and the rates of change of those variables. Now, we basically will have usually two equations. We have our constraint equation, and then its implicit derivative with respect to time. So the constraint equation can be used to find a missing value. So maybe if there's x, r, and h, you're given x and r, but you're not given h. Well, the constraint equation relates x, r, and h, so you can use that to determine the current value of h. And then when you differentiate that, you're going to have an equation that involves x, r, h, dx dt, dr dt, and dh dt. And then you'll be, typically in a situation like that, you'll be given two of the rates of change, maybe dx dt and dr dt, and then you know x, r, h, you know dx dt, dr dt, and you can use that equation to solve for dh dt. Another thing that I should note, and this goes back to kind of reading the problem, now that you kind of have maybe an abstract view of what's going to go on with these related rates questions, but it might say the length at that moment or at that instant is 5 feet or 3 inches or whatever it might be. So distinguish carefully. Just because you're given an actual number doesn't mean that that variable is a constant, right? So you might say at the moment when the boat is 5 feet from the dock. Okay, well, it's only 5 feet from the dock at that moment, but then its distance is decreasing because you're pulling it toward the dock. So you have to kind of use your imagination and really read the problem carefully to distinguish between a number that might be a constant, where, okay, that number is just not going to change, right? I mean, the Statue of Liberty is this tall, and okay, I'm moving my boat closer to the Statue of Liberty, so the angle at which I'm viewing the Statue of Liberty is changing, my distance to the Statue of Liberty is changing, but the height of the Statue of Liberty is not going to be changing, right? And it might say at the moment when you're 1.5 miles from the Statue of Liberty. Well, okay, you're 1.5 miles, but you're in a speedboat going toward the Statue of Liberty. So that distance is changing. So you see the difference is that some numbers are going to be just numbers that are constant, and others are just going to be the instantaneous value of a variable at that moment in time. So that's kind of a brief overview to some of the problem-solving suggestions for tackling these related rates problems. And in the next couple of videos, we're going to actually just go through some examples. A final note before I end this video, and that is, there's not one equation out there that you can go and find and say, that's the equation for my problem. Each problem is different, and the challenge to you is to gain practice looking at these different problems. So there's not like, it's not just like the same equation over and over again. Here's a physical problem. You have to really get involved and read the problem and understand it and see what's happening, draw a picture, and it's really ultimately up to you to come up with your own equations that model that particular situation. So you can look through any book you want for hours, and you're never going to find the equations that describe your problem, because it's a unique problem that it's up to you to model and come up with the equations on your own using these sorts of strategies. So anyway, as I mentioned, the next videos we're going to see some actual examples, so we'll take a look at what this looks like in action.